At 6:30 a.m. in South Africa's Mponeng gold mine, 30 miners step into a cage elevator that will drop them 4 kilometers straight down. In 12 hours, they will return having worked in 60 degrees Celsius rock temperatures, hot enough to cause severe burns on contact. They'll lose more water through sweat than most people drink in 3 days. Without massive cooling systems, they would die within minutes. This video follows their descent into conditions that actively try to kill them, showing how human determination meets the absolute limits of technology. Surface departure. The surface of a deep mine looks deceptively normal. Miners gather at the shaft headframe, a steel tower that houses the winding gear for the main elevator, but their equipment tells a different story. Each miner carries a personal breathing device called a self-contained self-rescuer strapped to their belt. This chemical oxygen generator can provide 60 minutes of breathable air if they need to escape through smoke-filled tunnels. They also carry emergency communication devices, multiple lights, and water bottles that will prove inadequate for what lies ahead. The ritual of descent begins with equipment checks. Cap lamps are tested for battery life and beam intensity. Self-rescue equipment is verified. Water bottles are filled. These aren't safety theater, they're survival preparations for an environment where equipment failure means death. Before stepping into the cage, miners receive a briefing on current underground conditions. Today's wet bulb temperature readings from the deeper levels, ventilation system status, any ground instability reports from the previous shift. The wet bulb temperature is critical because it combines heat and humidity, the two factors that determine whether human cooling systems can function. If readings exceed 28 to 32 degrees Celsius, depending on airflow, work stops. The human body simply cannot shed heat effectively beyond these thresholds. The cage itself is an industrial elevator designed to move dozens of people at once. As it begins its descent, miners know they're transitioning from a world where they can survive independently to one where they depend entirely on engineered systems. There's no gradual adjustment. Within minutes, they'll be in an environment where the natural temperature would cook them alive. First kilometer, the heat builds. At 1,000 meters down, the rock temperature has climbed to around 30 degrees Celsius. The geothermal gradient, the rate at which Earth's internal heat increases with depth, adds 2.5 to 3 degrees for every 100 meters of descent. This isn't ambient air temperature. This is the actual temperature of the rock walls surrounding the tunnels. Rock that radiates heat like a massive storage heater that's been running for millions of years. Miners immediately begin implementing their first survival protocol: aggressive hydration. They start drinking water before they feel thirsty because thirst is a delayed response to dehydration. In surface occupations, losing 2% of body weight through fluid loss causes noticeable performance decline. Underground, that threshold can be crossed within the first hour. The initial tunnels at this depth are spacious compared to the working areas deeper down. Main haulage drifts accommodate two-way traffic for 50-ton haul trucks. These trucks themselves contribute significant heat to the environment. A single large diesel machine generates thermal energy equivalent to hundreds of household heaters running simultaneously in an enclosed space. The heat from machinery compounds the geothermal load, creating localized hotspots that can push air temperatures well above the rock temperature. Miners traveling deeper notice the first signs of their body's response to heat stress. Blood flow increases to the skin to facilitate heat transfer. Heart rate begins to climb as the cardiovascular system works harder to pump blood through dilated vessels. Sweat production increases, though at this depth, it's still manageable. The body's cooling system is functioning, but it's already working harder than it would in any surface environment. This is also where the first critical infrastructure becomes visible. Massive insulated pipes carry chilled water from surface refrigeration plants. These pipes follow the main tunnels, branching off toward working areas deeper down. The water inside is maintained at temperatures just above freezing. Without this chilled water distribution system, the mine would be uninhabitable below 2,000 meters. Ventilation shafts separate from the main personnel elevator, provide the airways for the mine's respiratory system. Fresh air is forced down intake airways while contaminated air is drawn up through exhaust airways. The volume is staggering. Millions of cubic feet per minute circulated through underground networks that span dozens of kilometers. But even this massive air movement provides limited cooling at depth. The air heats up so quickly from contact with hot rock that it offers little thermal relief by the time it reaches the working areas. 2 kilometers. Engineering takes over. At 2,000 meters, rock temperatures reach approximately 55 degrees Celsius. This is where natural human survival ends, and engineering takes complete control. The ventilation air, despite being chilled at the surface, has absorbed so much heat during its journey that it provides minimal cooling effect. Mechanical refrigeration becomes the primary life support system. The chilled water infrastructure transforms from a supportive system to a critical one. Industrial cooling plants on the surface operate continuously, consuming enormous amounts of electrical power to chill water that will be pumped 2,000 meters straight down. These aren't residential air conditioning units scaled up. They're systems designed for major commercial buildings, but operated around the clock to support underground operations. 2 methods distribute this cooling. Bulk air coolers function like massive radiators placed in the main airways. Ventilation air is forced through these units, dropping its temperature before continuing to the working areas. But the more efficient method involves slurry ice, a mixture of chilled water and ice crystals that can be pumped through the existing water lines. When this slurry melts underground, the phase change from ice to water absorbs 334 kilojoules of thermal energy per kilogram. This makes slurry ice far more effective at removing heat than chilled water alone. Underground dams collect the melted ice water, creating reservoirs of ice-cold water that serve multiple purposes. Dust suppression sprays use this water to knock airborne particles out of the atmosphere before miners can inhale them. Machinery cooling systems circulate it through engines and hydraulic systems that would otherwise overheat in minutes. Localized air coolers positioned near work crews provide direct thermal relief to human operators. At this depth, miners encounter their first major physiological challenge. They begin losing 1 to 2 liters of sweat per hour. Their cardiovascular system shifts into overdrive, increasing heart rate and blood pressure to maintain circulation as blood vessels dilate to shed heat. The body prioritizes cooling over other functions, diverting blood flow from internal organs to the skin. This creates the first hints of the fatigue that will compound throughout their shift. Hydration becomes a disciplined routine rather than a casual activity. Water stations positioned throughout the mine provide not just water, but electrolyte replacement solutions. Sweat contains sodium, potassium, and magnesium, minerals essential for muscle function and nerve signaling. Losing too much disrupts the electrical systems that control heart rhythm and muscle contraction. Miners learn to recognize the early signs of electrolyte imbalance, muscle cramps, dizziness, and confusion that can escalate to life-threatening cardiac arrhythmia. The transition from 1 to 2 kilometers marks a psychological shift as much as a physical one. Miners move from an environment that's merely uncomfortable to one that's actively hostile. They begin the constant mental calculation that will dominate their workday, monitoring their body's response to heat stress while maintaining focus on tasks that require precision and attention to detail. 3 kilometers, the body under siege. At 3,000 meters depth, rock temperatures approach 60 degrees Celsius and the human body enters a state of controlled crisis. Miners are now losing fluid at rates that would be fatal if sustained without intervention. Over a 10-hour shift, total fluid loss can exceed 10 liters, more than 2.5 gallons of water lost through sweat. This represents a significant percentage of total body weight for most people. The wet bulb temperature becomes the critical measurement that determines whether work can continue. This metric combines heat and humidity to indicate whether human cooling systems can function effectively. High humidity prevents sweat from evaporating, essentially disabling the body's primary cooling mechanism. Mining operations maintain continuous monitoring stations that measure wet bulb temperature and have strict protocols for work cessation when thresholds are exceeded. At these depths, the cooling infrastructure operates at maximum capacity. The slurry ice systems pump constantly, delivering cooling energy measured in hundreds of thousands of kilojoules per hour. Underground refuge stations become critical safety infrastructure, pressurized chambers stocked with enough air, water, and cooling capacity to keep crews alive for several days. If main systems fail or emergency evacuation becomes impossible, miners develop a heightened awareness of their physiological state. They monitor urine color as an indicator of hydration status. They recognize the progression of heat exhaustion symptoms, initial fatigue and thirst, followed by headache and nausea, then confusion and coordination problems. The final stage, heat stroke, involves core body temperature rising above 40 degrees Celsius, potentially causing organ failure and brain damage. Recognition of early symptoms and immediate cooling intervention are the only defenses against this progression. The work environment itself intensifies every challenge. Production areas called stopes may have ceiling heights under 1.5 meters, forcing miners to work in cramped positions that restrict airflow around their bodies. The combination of physical exertion, confined spaces, and extreme heat creates thermal loads that push cooling systems to their limits. Miners must maintain focus and coordination while their bodies undergo controlled heat stress that would incapacitate untrained individuals. Communication becomes increasingly critical as environmental stresses mount. The constant noise from ventilation systems, cooling equipment, and machinery makes verbal communication difficult. Miners develop systems of non-verbal cues using cap lamp signals and hand gestures. A series of light flashes can indicate stop, go, or danger. These shared languages evolve within crews because split-second communication can mean the difference between life and death in emergencies. The buddy system transforms from policy to survival necessity. Crew members constantly monitor each other for signs of heat exhaustion, dehydration, or equipment failure. In an environment where individual collapse can endanger the entire crew, personal responsibility extends beyond self-preservation to active monitoring of colleagues. This creates interdependence that goes far beyond normal workplace relationships. 4 kilometers, maximum depth protocol. At 4,000 meters, the depth of the world's deepest mines, rock temperatures exceed 60 degrees Celsius. This temperature would cause severe burns on direct contact and kill unprotected humans within minutes. The cooling infrastructure operates at the theoretical limits of current technology. Surface refrigeration plants consume industrial-scale electrical power to maintain ice slurry systems that barely keep working areas survivable. The slurry ice systems at maximum depth pump continuously, delivering cooling capacity measured in megajoules per hour. The phase change from ice to water absorbs massive amounts of thermal energy, but the system operates with minimal safety margins. If cooling fails at this depth, evacuation must begin immediately because survival time is measured in minutes rather than hours. Working areas become increasingly confined as structural support requirements intensify. The weight of 4,000 meters of rock creates enormous pressure on tunnel walls and ceilings. Ground support systems use rock bolts up to 5 meters long, essentially stitching fractured rock layers together to prevent collapse. Steel mesh and shotcrete, sprayed concrete, create reinforced liners that contain loose rock fragments. Despite these measures, the constant settling and shifting of the rock mass create ongoing hazards that require continuous monitoring. Miners at maximum depth operate under the most stringent physiological protocols. Fluid replacement becomes a calculated science. They consume electrolyte solutions formulated specifically for extreme heat environments. Some operations monitor core body temperature in real time using sensors built into protective equipment. When temperature thresholds are exceeded, workers are immediately rotated to cooling areas regardless of task completion. The psychological demands at this depth are as challenging as the physical ones. Miners work in spaces where any system failure could be fatal, under rock formations that could collapse without warning, in temperatures that would quickly kill them if cooling stopped. They maintain concentration and perform complex tasks while their bodies undergo physiological stress equivalent to severe illness. The mental discipline required to function effectively under these conditions represents an extreme form of professional competence. Refuge stations at maximum depth are essentially underground survival bunkers. They maintain independent life support systems, including air filtration, water supplies, and cooling capacity. These stations can sustain crews for multiple days during emergencies when main systems fail or evacuation routes become blocked. The existence of these facilities acknowledges that at maximum depth, rescue operations face the same environmental challenges that make the work dangerous in the first place. The crew dynamics at this depth reflect the absolute nature of mutual dependence. Every action affects group survival. Individual fatigue or heat stress compromises collective safety. Miners develop almost telepathic awareness of crew status, recognizing subtle changes in movement, communication, or behavior that indicate developing problems. This group cohesion isn't just professional teamwork, it's a survival adaptation to an environment where individual failure means collective death. The limits we haven't solved. Despite successful engineering solutions for acute thermal hazards, underground mining continues to impose costs that technology cannot eliminate. The chronic health impacts represent unsolved challenges that accumulate over career-length exposure to extreme environments. Silicosis remains an incurable occupational disease caused by inhaling crystalline silica dust from quartz-bearing rock. Despite dust suppression systems using water sprays and high-efficiency respirators, fine particles still reach miners' lungs. The disease causes progressive scarring of lung tissue, leading to severe breathing difficulties and premature death. Coal workers face similar risks from coal dust, which causes coal workers pneumoconiosis or black lung disease. These conditions develop over years or decades, making them difficult to prevent through short-term safety measures. Noise exposure represents another unsolved health challenge. The constant sound from drilling equipment, machinery, and ventilation systems causes permanent hearing loss, even with hearing protection. The cumulative effect of 12-hour shifts in high-noise environments over multi-decade careers results in significant hearing impairment for most underground miners. Current hearing protection reduces but does not eliminate this damage. The psychological toll of extreme work schedules remains partially unaddressed. Fly-in, fly-out operations, where miners work 14 consecutive 12-hour days followed by 7 days off, create severe disruption down to circadian rhythms and family relationships. The constant transition between high-stress work environments and normal social settings creates isolation and relationship difficulties. While mining companies now provide mental health support services, the fundamental conflict between operational efficiency and human social needs persists. Heat management itself approaches physical limits as mining operations go deeper. The geothermal gradient is constant. Every additional 100 meters of depth adds 2.5 to 3 degrees Celsius of rock temperature. Current cooling technology can maintain survivable conditions to approximately 4,000 meters depth, but deeper operations will require breakthrough innovations in refrigeration technology or entirely new approaches to heat management. Some mines already operate at the edge of technological capability, where any equipment failure creates immediate life-threatening conditions. Ground control faces similar scaling challenges. Deeper mines experience higher rock stress and more unstable geological formations. While current rock bolting and support systems successfully prevent most collapses, the engineering margins decrease with depth. Some geological formations at extreme depth may be fundamentally unsuitable for human occupation, regardless of support technology. The economic sustainability of extreme depth mining also represents an unresolved challenge. The energy costs for cooling, ventilation, and safety systems increase exponentially with depth. The infrastructure investment required for 4,000-meter operations consumes enormous capital that must be recovered through resource extraction. As easily accessible mineral deposits are exhausted, society faces difficult decisions about the human and environmental costs acceptable for accessing deeper resources. These unsolved challenges don't diminish the remarkable success of current mining operations in managing acute survival threats. Engineers have successfully created survivable environments in conditions that would quickly kill unprotected humans. Miners have developed physiological and psychological adaptations that enable them to sustain performance under extreme stress. But the limits of these solutions are visible, and they define the boundaries of how far underground human industrial activity can extend. Each day, thousands of miners enter environments at the edge of human survival. They endure through advanced technology, strict discipline, and teamwork that makes survival possible. The supporting systems are immense. Cooling plants draw city-sized power, ventilation moves millions of cubic feet of air, and pumping ice slurry kilometers underground rivals space technology. The miners adapt by pushing their bodies to extremes, losing fluids at dangerous rates, working under heat that sickens most, and relying on group coordination where one failure could mean death. Their efforts show human ability to adapt, invent, and organize under lethal conditions. As surface resources dwindle, their work defines the frontier of industrial civilization. We should remember that every metal object you use comes from people who labored kilometers below in deadly heat. performing a daily heroism that sustains our world.